Welcome to my video series in which I aim to describe some of the most common supervised learning algorithms for parameter estimation in the physical layer of wireless communication systems. As I mentioned in my introductory video, this discussion is based on the public work of Mcclintick et al., which I have linked in the description below along with a couple other helpful references. This video is the first part of a video series that will describe some of the fundamental algorithms used for this application. Although this isn't an exhaustive list, I find this to be a helpful representation of the many algorithms that can be used, as well as some of their defining characteristics. For the purposes of this discussion, I will be focusing specifically on the convolutional neural network. So, let's jump right into some of the basics. In this tutorial, I will be stepping through each layer in a standard convolutional neural network. These being the input layer, the convolution layer, the max pooling layer, the ReLU layer, and the fully connected layer. But before I go into too much detail about any of these particular sections, let's talk a bit about neural network fundamentals. The fundamental building block of any neural network is the node. In a convolutional neural network, more from a theoretical perspective, a node is a feature, or filter, you could call it, that we desire to identify within the input dataset. From more of a mathematical perspective, a node is a function. This function calculates the weighted sum of the inputs through the use of convolution. So, how do we characterize this input dataset to begin with? This is where the first layer of the convolutional neural network comes into play. In the context of physical layer parameter estimation, these inputs could be any data known about the communication channel or even the operating environment. This data is then consolidated and it's used to form what is referred to as the input layer. This input layer data is then utilized for the identification of features. This identification, as I mentioned previously, employs the use of convolution, and therefore it's termed the convolution layer. So let's go into some further detail about how this works. So imagine you are given a set of collected and potentially inferred data regarding the communication channel and perhaps some system requirements. So let's call this data Y, where Y is completely unfiltered or altered. This represents the input layer of the convolutional neural network. So in order to form any neural network, the first step is to create features or nodes. These nodes are intended to replicate the function of neurons like in the human body. For this purpose, the convolution layer, also termed the feature extractor, is employed. In this layer, convolution filtering operations are applied to the data contained within the input layer. By this, I mean the data is filtered through the calculation of the convolution product of the feature and the section of data from the input layer that is being evaluated. So let's look at this mathematically. Let's assume that the input layer contains data in an n by n matrix. Now let's assume that the filter to be applied, let's call this W, is the size m by m. In this layer, the following operation is conducted. In simple terms, this equation sums up all of the input data after it has been weighted by the filter components. This factors in all of the contributions from all, if any, previous convolution layers. The result is an n minus m plus 1 by n minus m plus 1 matrix. This matrix is often called the activation map, and it contains a compilation of key features within the input layer data. The activation map is iterative, and each subsequent convolution layer contributes more and more features. Therefore, the more convolution layers that are within the convolutional neural network, the more of these features can be identified. So, as you can imagine, depending on the input data and the filters that are applied, there can be a large number of features identified in each one of these convolution layers. However, not all of these features are important or even relevant for a given parameter estimation problem. This is where the concept of the max pooling layer comes into play. Typically, in a convolutional neural network, a max pooling layer occurs between each subsequent convolution layer. After the first convolution layer, where the activation map is first created, the max pooling layer serves the function of filtering this activation map so that only the most important or relevant features are included. Now, the math behind this operation isn't too complicated, but it serves to significantly reduce this processing time. So, knowing that after each convolution layer, an n minus m plus 1 by n minus m plus 1 activation map matrix is created, we can divide this activation map matrix into smaller k by k sections. The max pooling layer finds the maximum of each of these k by k sections and just discards the rest. The result is an n over k by n over k matrix, which, as you can tell, is a significant reduction in the size of the activation map. Therefore, the number of features that have been identified. So this reduced activation map is then fed into the next convolution layer, and this pattern repeats until all of the convolution layers have been executed. So another layer that is commonly interleaved with both the convolution layer and the max pooling layer is the ReLU correction layer. So ReLU stands for rectified linear units. In this layer, the output of each convolution layer, seen here, is modified by the real nonlinear function represented graphically here. So this serves the effect of zeroing out all of the negative values contained within this activation map. The ReLU correction layer is referred to as an activation function, but that's not to be confused with any other activation functions that we're going to be seeing later down the train. So the final layer of all neural networks, including convolutional neural networks, is the fully connected layer. So this layer takes in the output of the final max pooling layer and calculates a vector of a certain size. Let's call this size S. So this size is dependent on the number of physical layer parameters being estimated for the given estimation problem. In the fully connected layer, each element of this input is multiplied by a calculated weight. Each element is then summed, and the activation function is applied to the products. The activation function that is applied is completely dependent on the size of what we've called S. So in the case that S is equal to 2, then we know that we're going to need to apply a logistic activation function. However, if this S, this size value, is anything greater than 2, we're going to know that we need a softmax activation function instead. So you can think of applying this activation function as, multiplying the input by a certain weight matrix. So this layer is called the fully connected layer because each input value corresponds to an output value. So at this point, you might find yourself asking, as I did, what is the difference between logistic and softmax activation functions? In addition to this question, you might be wondering how these weight matrices were determined to begin with. So to address this first question, a softmax activation function, or sometimes referred to as a softmax regression, is a form of logistic regression in which the input value is normalized so that the input becomes a vector. This vector has a probability distribution whose total sums to 1. This serves the purpose of restricting the possible output values to be between 0 and 1. This allows for the classification of more than just 2 parameters. This is a limitation of logistic regression, which is limited to only binary classification. So now let's look at the softmax function in a little bit more detail. In this function, we can see that we are taking the exponential of the input parameter and dividing it by the sum of the exponential parameters of all of the values that make up this input parameter. In this case, theta is equal to the transpose of the weights matrix, W, multiplied by the feature matrix. It's important to keep in mind that the goal of using an activation function to begin with is to determine if the trained set of features belong to a particular class. In terms of physical layer parameter estimation, this class would be a select parameter. Now we want to explore a little bit about where these weight matrices come from. Weights are determined through what is known as the backward propagation of the gradient. This is mathematically complex, and for your reference, I have outlined the basic steps to accomplish this. So this is going to be a very basic overview. However, more detailed explanation can be found in some of the references that I've linked in the description below. So first we need to know that there exists an error function. In this case, we'll call this error function E. We also know that each convolution layer that exists within this given convolutional network also has an error value associated with it. Starting at the convolution layer, which has known error values, we need to work our way backwards in order to determine the error of the previous layers. This is represented as the partial derivative of E with respect to the output of each node. And ultimately, we need to determine the weight matrix. The first step that is required is to find the gradient components of the weights. This can be done by applying the chain rule as follows. Next, the deltas need to be computed. It is important to remember that the delta of the convolution layer is known. This computation can be completed like so, where phi represents the activation function. Once the gradients with respect to the weights are determined from the convolution layer, errors need to be propagated backwards in the neural network structure. This can be done with another application of the chain rule, as shown here, where WAB is the weight or the filter applied. Hopefully, if you have found this description to be helpful, I highly recommend that you take a look at the references I've linked below. For more algorithm discussion, take a look at some of my other videos, and thank you so much for listening in.